All right, let's talk about one of the most extreme objects in the entire cosmos, quasars. These things aren't just bright. They're the unbelievably powerful hearts of ancient galaxies. And they hold some major keys to understanding how the universe itself grew up. So yeah, let's dive in.
So right away, we run into this massive paradox. A quasar's light comes from a region of space that's no bigger than our own solar system, and yet it can blaze brighter than our entire Milky Way galaxy thousands of times over. So how is that even possible? That one question kicked off a cosmic detective story that took astronomers decades to solve.
To get this, we've got to go back in time. We're talking the 1950s. The field of radio astronomy was just getting started, and these brand new radio telescopes were picking up these incredibly powerful signals from deep space. But when astronomers aimed their regular optical telescopes at those same spots, they found something that made absolutely no sense.
And here was the problem. Through a normal telescope, these things just looked like faint, boring little stars, points of light. But the radio signals they were blasting out were just immense, way, way beyond anything a normal star could possibly produce. This complete contradiction is actually where they got their name: quasi-stellar radio sources, or, quasars for short.
For years, nobody could figure these things out. Were they some new type of star right here in our own galaxy? Or were they something else entirely? The real key to cracking this whole case was figuring out just how far away they were, and that set the stage for a massive breakthrough in 1963.
So after these radio sources were all cataloged in the late 50s, astronomers tried to analyze their light. But the spectrum, when you break the light down into its rainbow of colors, it was just this bizarre, unreadable mess. Nothing matched. Then, in 1963, an astronomer named Martin Schmidt pointed the giant Hale telescope at one of the brightest quasars, a thing called 3C273, really hoping he could finally find an answer.
Okay, before we get to Schmidt's big discovery, we need to quickly wrap our heads around a crucial concept: cosmological redshift. Just think of it like the sound of an ambulance siren. As it drives away from you, the sound waves stretch out, and the pitch gets lower, right? Well, with light, a similar thing happens. Because the universe is expanding, light from distant objects gets stretched out on its journey to us. This stretch shifts the light toward the red end of the spectrum. And here's the key: the more redshifted the light is, the farther away the object is.
And this was Schmidt's incredible aha moment. He suddenly realized that the weird, unreadable pattern in the quasar spectrum, it wasn't some strange new element at all. It was the totally familiar signature of plain old hydrogen, just stretched or redshifted by a truly massive amount. The pattern was there the whole time, just in an extreme disguise.
That redshift told him the distance, 2.4 billion light-years, and that was the bombshell. 3C273 wasn't some strange star in our cosmic backyard. It was an object of almost unimaginable power, way out in the early universe. To be visible at all from that far away, it had to be astonishingly, unbelievably bright. So the distance mystery was solved, but it opened up an even bigger question: what in the universe could possibly be that powerful?
And the implications here were just profound. See, back then, the Big Bang Theory had a big competitor called the steady-state theory, which basically said the universe was the same everywhere and at all times, forever. But since quasars were only found really far away, which means we're seeing them as they were in the distant past, it proved the universe changes, it evolves. This was a massive piece of evidence in favor of the Big Bang. Okay, so we know quasars are incredibly distant and powerful. But that brings us right back to our original question. What is the engine driving all of this incredible energy? I mean, how does it actually work?
Well, it all comes down to this four-step process. First, you have a supermassive black hole. We're talking millions or even billions of times the mass of our sun, sitting at the heart of a young galaxy. As it pulls in all the nearby gas and stars, that material doesn't just fall straight in. It spirals around, forming a cosmic traffic jam called an accretion disk. The friction and the gravitational forces in this spinning disk are so extreme that they heat the material to millions of degrees, causing it to glow with just a ferocious intensity. That's the light we see.
Now, to put the efficiency of this thing into perspective, just think about our sun. It's powered by nuclear fusion, and that process converts only about 0.7% of its mass into energy. A quasar's accretion disk, on the other hand, can convert a mind-boggling 10 to 40% of the mass falling into it directly into energy. It is by a huge margin.
the most efficient engine that we know of anywhere in the universe.
Now, over the years, astronomers have observed all kinds of different active galaxies. You've heard the names: Quasars, Blazars, Seyfert galaxies. For a long time, they all seemed like totally different kinds of beasts, but it turns out many of them might just be the very same thing, just seen from a different angle. This idea is called the unified model. Imagine the central black hole engine is surrounded by a big dusty donut, what astronomers call a torus. Now, if we happen to be looking straight down the hole of the donut, we get a perfect, clear view of that blazing accretion disk. That's what we call a classic quasar. But if we see it from the side, the dusty donut blocks our view of the very center, and we see a less intense version. And then there's the really wild one. If we just happen to be staring right down the barrel of a jet of particles being shot out from the black hole's poles, all that radiation is beamed right at us. And that's when we see an intensely bright, super-variable object called a blazar. It's all about perspective. So, because these quasars are so incredibly bright and so ridiculously far away, they aren't just fascinating to study on their own, they're also one of the best tools we have. Modern telescopes, especially the James Webb Space Telescope, use them like cosmic lighthouses to probe the vast dark emptiness of space.
Here's how this works. As a quasar's light travels toward us for billions of years, it passes through all these invisible clouds of hydrogen gas that are just floating out there between the galaxies. Every single cloud it passes through takes a tiny little bite out of the light at a very specific wavelength. So by the time that light finally gets to us, its spectrum is filled with this whole forest of dark lines. It's like a cosmic barcode that tells us exactly where all that invisible gas is, letting us map out the hidden structure of the universe. It's genius.
And the latest discoveries? They're pushing our theories to the absolute breaking point. The JWST is finding quasars so far back in time, like this one, GEZ11 from just 400 million years after the Big Bang, that we honestly can't explain how their central black holes grew so massive so quickly. It's like they skipped a few steps. This is completely rewriting the book, and it suggests the very first black holes might have been born much, much larger than we ever imagined. And this brings this whole incredible story right back home. It's important to remember that being a quasar is really just a phase in a galaxy's life, when there's a lot of fuel available. Most big galaxies, and that includes our very own Milky Way, have a dormant, quiet supermassive black hole at their center today. Which leaves us with one final, fascinating question. Billions of years ago, was our own galaxy's core a blazing quasar, shining as one of the brightest beacons in the entire universe? The answer is, yeah, very possibly.